In this unit, we're going to talk about high availability, disaster recovery, and business continuity. And these are terms I think that a lot of people throw around, and sometimes we don't think about what they actually mean, right? So, what is the difference between business continuity and disaster recovery and high availability? And really, conceptually, these are all just words, right? But the way the industry typically views this stuff is business continuity is the overarching concept, right? So all these other terms that I just threw out, like a disaster recovery and high availability, they all fit into the business continuity models, right? So when we talk about business continuity, it's a collection of lots of different activities and policies and governance that help us define how we're going to ensure that we have resilience in our IT systems, right? So some of the things that we do, impact analysis. That's where we think about what types of things can happen. We analyze the risk and assess the risk, and then try to figure out what we can do about that risk. So that's where our disaster planning comes in, right? So impact analysis is what can happen, what's the impact going to be, how much is it going to cost us, and then we figure out what's an appropriate, what are appropriate measures we can take, and how can we plan for those eventualities. And I think a lot of us do this every day in our lives, right? We do this every day, with our homes and our vehicles and so forth. We're constantly analyzing what our risks are and trying to figure out what's an appropriate response to those risks. There's lots of things we can do to protect ourselves, but some of them are just overkill, right? Um, when you think about your home, I think the average home or the average structure in the United States burns every 100 years, right? There's a fire about every 100 years in most structures. So, those are pretty well understood odds. Although I think that's going down considerably with all the enhancements to, fire suppression and materials that are manufactured today don't catch on fire as much, right? But the point is that we can assess those risks. We have a pretty good idea of when something's going to happen. We have a pretty good idea of what it's going to cost, right? So take your home, for example. I know that I can insure my home against a loss from fire, and it might cost me $1,000 a month, right? And I know that a brand new house is going to cost me with all the contents. Maybe that's going to cost $500,000. So is it worth it to pay $1,000 a month, because to protect yourself from a fire? And most of us are going to live in a home for maybe 30 years, right? So let's say it's 30 years. That's a lot of months. Is it going to add up to to the $500,000, right? It's probably pretty close, right? We could do the math. Um, it's 60,000 every 5 years, right? So you can kind of figure this out. But I think most of us think that that's probably a good investment to get insurance, right? Because we know something is going to happen in that time. Maybe not a fire, but maybe a flood or something like that. The other part of disaster planning, it's not just planning, in the sense that understanding what can happen and how we're going to mitigate that, but also having actions that you can take in the event of a disaster, right? When I was a kid, I was a lifeguard, and they used to tell us that when somebody was drowning, you can't say to a crowd of people, somebody go call 911. You have to point to someone specific and say, you go call 911. Because in a tragedy, a disaster, when things are confusing, people don't tend to, if they don't know what to do, they kind of freeze, right? They don't really do anything if they're not sure what to do. But if you have a clear plan, it kind of puts you in autopilot. You just follow the instructions and you know exactly what to do. So again, it's what's an appropriate level of protection, right, based on the risk is what we're thinking about, and that's all kind of soft stuff that happens. One of the things they talk about is recovery time objectives, and there's a whole lot of other concepts with business continuity. I just kind of cherry pick things that I think are relevant to database management. One of them is recovery time objectives, and this is where we want to find out, when a resource goes down, what is the expectation for how long it's going to take to restore it back to full operations? There's a lot of variables there, right? How critical is the system? Um, you know, what kind of hours is it being used, right? Maybe there's downtime, overnight or something like that. So I work a lot in the healthcare industry, and there are some systems in healthcare that our recovery time objectives can be a full day, right? If email goes down, it's okay if it takes time for that to come back up because it's not critical, right? But then contrast that with a system that's used in the surgical suite, right? That's used during surgery. If that system goes down during surgery, it's important that it's back online as quickly as possible. Otherwise they have to cancel the surgery. And, there could also be catastrophic effects if somebody has a life-threatening injury and they can't continue surgery, then, the patient could die, right? Strokes and things like that, with medical imaging, a lot of those things, our recovery time objectives are very low. So again, we have to assess, what is the uptime that we need and how quickly do we need to get those systems back online. So it's one of the ways that we assess, whether or not or how we're going to, what's an appropriate level of protection to mitigate that risk. And then continuity planning, which is, what can we do to plan for a disaster, to make sure that we continue operations, right? So continuing operations through a disaster is continuity planning, I guess is a good way to put that. And there are lots of technologies that can support us on that to a varying degree. And I want to talk about that and how we handle this in sort of in the database world and the application support world. And if you think about, so far in this class, as we've been working with our databases, we have essentially a single server, right? So we have this virtual machine that's in Google Cloud or wherever you built your virtual machine to do your exercises. And within that virtual machine, you have the database engine. You've got a disk where you're storing the files, and you could have an application, right? We haven't really built any applications in this class. We're just using the console in SQL to work with the database engine. But as most of you know, that's not typical in the real world, right? In the real world, users aren't interacting with a MySQL client, right? They're using a web application or a desktop application, mobile apps, and so forth, and they're connecting through some API, through web services and web APIs and all that other stuff that we talk about. I think we covered this in a little bit of detail in Info 365, the follow-on to this course. So all of that stuff in our labs and our practical assignments have all been on one machine, right? And if you think about it, if that were how we did things in production, and going back in time, there's and not even that far back, right? There are people that still do this, right? If it's not a critical application, you might have just one server that has all of the stuff that you need for an application, including the database and the data itself, all on disk, all encapsulated within a virtual machine or within a single instance of a virtual machine, or even on a single physical machine. And in that scenario, if let's say your disk fails, right? Let's say the file gets corrupt. It doesn't have to necessarily be a disk failure. It could just be that the files somehow get corrupt. If that happens, you're down, right? The application is no longer working. So this is not a tenable solution for most of our IT systems that are, anything more than just desktop applications. When we have many different users all relying on that application in a server environment, the expectation is we can't just have a single disk with our data, right? We need to have something a little more substantial, a slightly more substantial infrastructure. So the way this usually plays out is we use something like a SAN or a NAS. And by the way, a SAN and a NAS are very similar. You may have learned about this in other classes, but they're basically the same thing. You've got a collection of disks, right? Usually those disks are using RAID. RAID is basically redundancy. And what that means is if we lose by the way, our data storage goes away on our server. But if you lose a disk with RAID, it still runs, right? It's impervious to a failure of a single disk. But at some point, if you lose too many disks, then you have corrupt data. But the idea here is that you get some degree of business continuity with, or high availability, I should say. You get some degree of high availability by having multiple disks with some redundancy. And I want to get into exactly how this works. I have another presentation in YouTube that you can probably dig up that talks about how RAID works. It walks you through, how striping works and all that stuff if you want to learn about it. But the important takeaway here is you've got multiple disks, much faster performance because you have multiple disks, and also you have fault tolerance because you have many disks. So you can lose disks and not lose your data as long as you replace those disks, or have some process in place that automatically replaces those disks, which some systems do, right? When they fail, they have hot spares ready to take over. I was going to tell you the difference between a SAN and a NAS. A SAN basically is a platform of disks that you mount over a network. So it's wholly controlled by a single front end server, right? So a front end server controls that disk. It controls the SAN as if it were a local disk, but it's not a local disk. It's actually a managed storage device somewhere else. And that managed storage device could be shared by many different platforms, right? So many different application or database platforms could all be sharing that shared SAN, but each one gets a little chunk of that shared SAN that they own and they manage. They're the only ones that have access to the data within their own little chunk within that. And usually this is supported by things like Fiber Channel or iSCSI. And again, I've got some videos that you can learn about Fiber Channel and iSCSI and how it works, where you would use it, and so forth. A NAS, on the other hand, is a little bit different. That's where um, it's a fully managed disk platform, uh, but many different systems can connect to it. So the file system is managed by the disk subsystem itself, as opposed to a server or an application that's using it, right? So what that means is when you write a file to a NAS, anyone else that can also connect to that NAS and read the file back, and likewise they can write files that you can read. So in the common vernacular, you might call that file sharing, right? If you had a Windows computer and you set it up on a small network and you turn on file sharing, what you essentially have is a NAS, or what I would call a poor man's NAS. So a SAN is more like a hard drive that you happen to connect over a network. That's all. Or it's a hard drive you connect over the network that lots of different people can have different parts of that hard drive, more or less. But what that means is that you can use any file system you want when you use a SAN. With a NAS, you're kind of locked into whatever the storage platform supports. But anyway, that's enough about the storage platform and storage technologies. But either way, we have this robust storage technology that we're sort of hanging off the back end of that application and database server. We might still have our application, our database on the same server, but it's pointing to some storage engine, some storage platform that we're using on the back end. Now, if, for example, so what this gives us, by the way, when we have this one storage platform with many disks and it gives us that fault tolerance is not necessarily business continuity and disaster recovery. It's just fault tolerance, right? That subsystem could still fail. That whole NAS or that SAN could still go down. And if that happens, we lose access to our data. So one way we can mitigate that is having a whole secondary storage platform where we do block level replication. So you might hear that term block. I should have put that on the slide here, but block level replication is where our storage platform, our file storage platform, is managing the replication of files from one system to another. And in your book, they actually talk about doing this, right? So one of the backup methods that they talk about is file backups, where you take the physical database files and you replicate them to a completely separate disk system, right? So you could do a file level. It's it's a physical a physical backup. So that's another way to do this. Now, one problem though here with this method, right? So our database server is pointing to that storage platform on the bottom of the screen. When that storage platform goes down, that platform has to have some way to use the other storage platform. We also still have a single point of failure with the database engine, right? So this is where we start talking about what level of redundancy and what level of high availability and resilience is appropriate for whatever application we're working with or designing, right? So right now, we have at least protected ourselves from data loss in this scenario. The database engine's working just like we've been playing with it in our labs, but if rather than being a local disk, we move it to a storage platform. If that storage platform goes down, we could also have replication. So Google could do this for us, right? If we build our if we build MySQL in Google and we use a disk that's actually not a local disk, but it's actually a disk in the cloud. If you think about this, we're actually already doing what's on the screen in our labs, right? Because our disk that we use in our VMs that MariaDB is using, if you go and read the terms of service in Google Cloud, that disk is actually replicated 3 times within their data centers. I think they guarantee that it's replicated across 3 different zones or something like that, right? Or maybe it's 3 different disks within their own data center, whatever it is, right? But they're doing that replication for us, so we can't lose that data, or at least it's very unlikely that we're going to lose that data. But we still have a single point of failure. We still have that database platform. Oh, by the way, this is sort of business continuity, right? What we're talking about here. Um, so let's say we lost the database server, right? So you built your virtual machine, right? For your practical assignment, and you've got your little MariaDB, and you've got some application that's using MariaDB. Maybe you wrote something in PHP or Perl or Python or Java or whatever, right? You lose the database. That application no longer has access to that database, and it's down, right? So this is another point of failure. So what can we do about that? Well, one thing we could do is instead of having our database run on the same machine as the application, we create a more high availability scenario by having two database servers, right? So we have two database servers now, and each one is pointed to its own storage platform. So each one of these database servers has its own storage backend. Um, in order to make this work, in an automated way. So now that application that you see on the screen, in order for it to really take advantage of this architecture, it would, instead of using the IP address or the host name of a single database server, it goes to a load balancing switch. So that line that you see on the right side of that load balancing switch coming out of the application server would go to what we call a virtual IP or a VIP, right? So it's a virtual IP on a load balancing switch or a content switch. This would be something like an F5 or an A10, or there's a whole bunch of companies that make these. Coyote Point, the old ones. A Linux box could do this, right? You could build your own, roll your own load balancing switch in Google if you wanted to, using Linux. But in any event, all the requests to the database go to a virtual IP on the load balancing switch, and it sends all of those requests down the active uh, connection. So that's the arrow pointing down to the left. That's the active database, right? Now, let's say that active database were to go down, then the request would go to the passive, right? So it's an active passive failover, meaning that in normal operating conditions, all of the traffic is going to the active, and when there's a failure, everything goes to the passive, right? That's one way you could do this. Um, as far as this is more sort of business continuity, right, or fault tolerance, but you could also add an element of high availability here. I don't have it in the diagram, but let's say you had many database servers. You could have one that is um, for data manipulation. So your update, insert, and delete, and then all of your selects could be going to any one of many of the slaves to that master, which we're going to learn about here in just a few minutes. I'll talk about how replication works. But the problem is with traditional replication, you have to or traditional active passive, you always have one active and then you have a passive, and then you can have many passives, but you roll over to those as they fail. One of the important differences here too is by the way, the database server goes away, right, on the server. But so on the right-hand side, you saw before we were doing a block level replication from one SAN or NAS to the other SAN or NAS, right? So from the bottom one to the top one, we're doing, our storage platform is doing some kind of replication for us, and it's the file level. That goes away when we add more database servers. That now we want to now manage that from the database server itself. So this is what replication is doing. So with replication, all the transactions that are happening on the database at the bottom are being replicated to the database at the top. That way, if the database on the top of the diagram, the bottom of the diagram, if that were ever to go down, either down for maintenance or down because it failed, all the traffic starts moving automatically to the server on the top, and everything is there because it's been replicated. But we're no longer doing a file level copy. Instead, the database engine is notifying, the one on the bottom is internally notifying the server at the top that here are some changes to the actual data, and go and make those changes on disk, right? So it's not a block level storage replication. Now it's logical in that, it's maybe it's SQL commands or, it's some other method, but we're going to talk more about how this works in just a few minutes when I get to that with the replication. But the replication is a little bit different than block level, right? So this is the next level of redundancy that we could, or fault tolerance that we could build into, into our platform. We could also add disaster recovery to this, right? So I think right now, in my view, this is, when we use replication and we have two storage platforms in an active passive failover, this is sort of business continuity. It's high availability, and it's an element of fault tolerance, but But sometimes we need even yet another layer of redundancy, and this is where your disaster recovery might come in. So for disaster recovery, we could either take block level copy and put it on tape, right? And I know tape sounds really primitive. That's actually, I kind of drew a picture of a cassette tape there. Um, maybe that's a sweet mixtape from the 80s, but um, but we're copying that data to some other platform, and it's for long-term storage, right? We're not using that data day to day. That's why I made it, my picture, it's a tape, because it's not for day-to-day use. It can be slow because it's only there for a really bad day, right? Maybe the data center burned down, right? Or a flood, or something happened, or maybe there was an attack and you lost all your data from ransomware, or who knows, right? And to some extent, it's good to have this sort of insulated long-term disaster copy sitting somewhere. And again, this could either be block level from the storage platform, or probably arguably a better way to do this is it's managed from the database. So you can do these managed backups from the database, and it can be creating these database backup files that are being stored. And the nice thing about doing backups, unlike replication, right? So with replication, you're typically going to have, pretty close to real time changes happening in all of the systems that you're replicating to, and it's really for real time use, right? With backup, you could do incremental backups. You could do all different types of backups, such that, let's say somebody accidentally deleted a record 2 weeks ago, and you need to get those records back. With backups, you might have a scenario where you have snapshots from 2 weeks ago and a month ago or 6 months ago, right? So you can go back in time to repair things that happened in the past, right? All is not lost, if you have a good backup strategy. So that's kind of one of the advantages of backup. And one of the other things too about backing up is, when we talk about disaster recovery, there's also the cloud, right? So, if I were teaching this class 15 years ago, I would tell you that tape is the de facto standard for disaster recovery. But I think in the industry, in the field, we're starting to see that change. We're starting to see more and more folks using the cloud as their disaster recovery layer. And, when you think about it, the cloud is, there's this, it's interesting because the cloud is starting to become more of that data center model, right? We're moving data centers to the cloud. We're starting to see more and more infrastructure being moved to the cloud. But without a doubt, disaster recovery in the cloud has definitely is a stronghold right now. We're seeing less and less tape. We're seeing less and less redundant storage on-prem. It makes a lot of sense to use the cloud. But I think we're still not quite there in the cloud for production use for a lot of business applications. I think that's still evolving. I think we're going to end up there, but it's still evolving right now. I think if you took the temperature in the industry, you would find that a lot of applications are still hosted on-prem for a lot of large organizations and things like that. Especially in my industry, which is healthcare, the cloud is really kind of slowly taking hold, but we don't see a lot yet. So anyway, this is basically, now with our database, we have almost, kind of almost the best case scenario. Now there's one other layer we could add onto this for the database. Instead of doing replication, what if my server on the bottom fails? That means I have to roll over to the server that's on the top. And that's okay, right? That's an understandable scenario. But my other option here is to cluster. There are two reasons that I would do clustering. One, clustering is nearly real-time synchronous replication, right? So it's very similar to replication, except it's real-time. And we're going to look at this in more detail here in a few minutes. So one reason is the real-time, but the second reason that we would do clustering as opposed to replication is that they can all be active at the same time with clustering. With replication, it's active-passive. With clustering, they're all active, all at the same time, and they can all handle any transaction, not just, in replication, the top one would probably be read-only. You wouldn't be doing manipulation of data on the top one. And the bottom one, with the clustering, any one of those nodes can handle a delete, an insert, an update. Changes to the schema could happen on any one of those servers. So now my application, when it's talking to the database, doesn't matter which one it connects to. It can do all the transactions that it wants on any one of those nodes. Any of those nodes could go down at any time, and no one would even notice, right? Anything kind of like RAID, right? Where any disk could fail and no one would know. Kind of in the same vein, right? So any one of those application nodes could go down and it wouldn't matter. No one would care. I mean, somebody would care. Hopefully, the system administrator would care, right? But users wouldn't notice, which is the important part. So we have real fault tolerance. We have very high availability when we use a clustering model. So again, we have any type of transaction, and it's very near to real time. There is no master, right? There's no, it's a little bit more resilient, I think, than even replication. So one last thing on this diagram is we have that single app node on the right-hand side. In the real world, you would probably also cluster your applications, right? So the application would also be clustered. So you'd have multiple nodes for your application, all again going through this load balancing switch. And I don't have it on the diagram, but you would probably have a load balancing switch in front of those applications as well, right? And that would give us a very robust infrastructure for whatever application we're trying to support. You would have multiple application nodes, you have your multiple storage nodes, you have your multiple database nodes. You may even have multiple load balancing nodes that can load balance to each other. We can go on and on, right? But again, when I talked about in that first slide, this sort of the appropriate level of redundancy, right? I talked about that. It's one of the things that we have to think about is, what level of redundancy is appropriate? What level of high availability is appropriate? Maybe you don't need to have clustering. Maybe you don't even need to have replication. Maybe the file level backup is good enough, right? So I talked about a couple different, as far as high availability, I did talk about some of this stuff already, but there's really, as far as database backups, your book talks about three methods with MariaDB, and these are pretty common across most of the database engines. You've got the file-based backups, where you manually back up database files, from one machine to another. But usually those files are locked into the version or instance. In some database engines, you can't take a database file and move it from one instance to another and expect it to work. You have to actually detach and reattach that file to another instance and then go back the other way, right? So it's not a seamless process to create and use those backup files, right? And also, it's not uncommon that you'll have a backup of a file, but you've upgraded your database 5 times, and now that backup is unusable to you because it's not backwards compatible, right? So that could be a challenge as well. So a slightly better option is to use the SQL dump utility. Most database engines have some equivalent to SQL dump, but basically in MariaDB and MySQL, it creates a text file that is all of the SQL statements that you would need to completely replicate that database, right? So it's every SQL statement. So it's almost as if you're sitting down in front of the computer and you're going to build your database from scratch again. It creates the file that you could use to basically build the database from scratch. Um, Obviously, with a very large database, it can take a while for it to output and create these files. It can take a while to run them. Sometimes you have memory problems when you run these, but there's some ways to mitigate that your book talks about. Some of the options with the SQL dump utility or the MySQL dump utility. Um, Nice thing about it is you can execute them in any other database instance. They're typically not bound to a specific version of MySQL or MariaDB. In fact, in many cases, you can even run them on completely different database engines like PostgreSQL or Oracle or something like that, and you can port them. And then you have flat file backups, which is where it's very similar to a SQL dump. In fact, use the same utility, use the MySQL dump utility, but instead of creating SQL statements, instead you're outputting just the data, right? So a SQL dump, the second option I talked about, it creates the SQL statements, but it's both the data definition language, in other words, the schema for your database, and then it's the insert statements to actually build that database, right? That's what a typical SQL dump will look like. Whereas the flat file backup, it's the structure is sort of baked into the output because it's outputting a CSV or a tab delineated file, which you can then import to some other database engine. And this is typical if you're not sure what database engine you're going to be re-importing it to, or if you're not sure what you're going to be working with. The file-based backups, those are physical backups, right? So they're physical files. We typically refer to that as a physical backup. And then the other two I talked about are your logical backups. Logical in the sense that you're not physically moving blocks, right? It's not blocks of storage moving from one device to another. It's not a bit for bit or byte for byte copy. Whereas logical all you're doing is taking the logically what's in that database and you're recreating it in the other system. It's not, so you're going to end up with a different type of data file, right? Potentially. It may be very similar, but it's going to be a different data file. It's going to be built in a different way, right? Even if it's close to identical, it's still going to be slightly different. So that's a physical versus logical backup. So as far as physical file backup, first, if you're going to do a physical file backup, it's generally a good idea to go to read-only mode, because it's difficult for the file system to interact with those files while to cleanly copy the files while there's active operations. But when you do go to read-only mode, users can still select. They're just not going to be able to update, insert, delete. They can't create user accounts. They can't create tables. They can't do any DDL type statements. They can't alter anything, right? But they can at least do their select statements. So it's better than being down, right? And the files that have to be copied, generally, if it's InnoDB, you're going to find them under in MySQL or MariaDB by default. They're in varlib MySQL and then in a folder that's the database name. InnoDB is a table level, right? So it uses table level files, meaning that for every table you have in your database, you're going to have a file representing that table, two files representing each table. One of them is going to be the table definition, the other one's going to be the actual data. I talked about, a couple minutes ago that if you output a flat file, like a CSV or a tab delineated, they're sort of self-describing, right? You don't necessarily need that data definition language if you have a CSV because the columns are all kind of declared across the top, right? The first row is all your column names, then you have all of your data, and that's really kind of the structure baked in. But what you're missing is things like foreign keys. You wouldn't really know any of the rules or around that data or constraints. That wouldn't be in a CSV, a constraint, for example. You're not going to know what a primary key is from that. So a lot of those things might be missing. So to that point, in theory, if all you have is the IDB file, the data file, theoretically you can use that to import to another MariaDB instance, and it will work in theory. But it's best to also have the .frm file, which is the data definition, or the data definition file. So you want to have both of those if you can. But if you only have one, if the other one gets corrupted, it'll probably still work. As far as a logical backup, like I talked about before, the MySQL dump utility is the de facto standard for that MariaDB and MySQL. There are very similar utilities for Oracle and Microsoft and PostGre. A lot of them have very similar utilities. And by the way, their structure for the files is very similar as well. I will say that I think some of the other database engines, you'll only find one file for the entire database as opposed to individual table files, right? So sometimes you have those little idiosyncrasies or differences between database engines, but the concept is very similar. So as far as the MySQL utility goes, the MySQL dump utility, it's going to create a text file, which again, it contains the SQL commands to build the database, and it's also going to have the insert statements. Both of those are optional, though. You could have a MySQL dump that contains only the data, so just the insert statements. You could also have one that only has the schema with no insert statements. So you can do it either way. Or you can have everything in there, right? You can even limit it to only outputting SQL statements for certain databases, and well, by default, it's only one database at a time. But you can also limit what types of objects or what objects it outputs. So you can list all the objects you want, or you can list objects that you don't want. You can tell the utility, give me everything except for these two tables, right? Leave these two tables out, but give me everything else, right? So it's pretty granular. It definitely gives you a lot of control of what it outputs. There are some options with it that I just wanted to talk about real quick. One is there's some options that have to do with replacing data. And this is where, let's say you want to, you've got two databases and you want to take all the data from the first database and you want to import it to the second one, but you don't want to lose the data that you already have in the second database. So replace should do that for you. It should just, if any of the rows already exist in the destination, it's just going to skip those rows. But and if you skip down to the bottom here, one of the issues with that is the auto increment sometimes, right? By default, when you do a SQL dump, it's going to keep all of the primary keys that are auto increment the same, which is important because if you have foreign keys, then you're going to want those to all be the same. But if you don't have foreign key relationships defined in your database, right? So when you created these tables, if you didn't define the foreign keys, then they're all going to be broken if you use the replace option, or if you don't allow auto increment. If you don't keep the auto increment values, which by default you can when you do a replace because they may already exist in the other database, right? Um, so in that scenario, you're going to lose all of your foreign key references, and it's going to ruin your day. Um, However, if you defined all those foreign key references, then MySQL dump can sort that out. It's just going to take much longer for it to run, but it's something you need to be aware of. And also, you have the ability when you do a SQL dump, you also have the ability to lock the table while that's happening, or lock all the tables. So it'll basically, we talked about transactions earlier in the course, but basically it's going to prevent anyone from doing data definition or data manipulation while the SQL dump is running, either when it's exporting or when it's importing. And that could be important for example, setting up replication. I'm going to talk about that in the next slide after this. Um, there's other formats that SQL dump can dump to, and I talked about this in the slide before this one. We have these SQL dump files, but you could also use the MySQL dump to create CSVs and tab delineated files. And these are useful, I think, if you're outputting this data to import it to another MariaDB or MySQL server. It makes a lot of sense to use the SQL dump, right? To use the MySQL dump because it's going to give you statements that you could just run. It's just going to work, right? But if you're not sure what database engine, or if it's not MariaDB or MySQL, and you don't want to have to go through the work of porting all the SQL statements to a different syntax, then CSV and tab delineated might make more sense for you, because almost every database engine has some tools available for importing from CSV or tab delineated if they're well structured. And even if they're not well structured, right? So if you took Info 365, one of the things we played around with in that class is what to do with all this data when we have to build a new database. Usually we don't just build the database and start from scratch. We're almost always given a backlog of data to start with, right? So how do we deal with all that, right? So there's lots of tools out there and techniques to do that. The point is that it's possible, right? It's possible to work with data when it's a CSV or tab delineated, but it's going to be much more difficult if somebody hands you a bunch of SQL statements and you don't have that database engine to run those SQL statements, or if any of them are corrupt, or what have you. So sometimes this sort of agnostic format, CSV or tab delineated, is a little more robust for other applications. So certainly another option to be aware of. So let's fast forward now to replication. I'm gonna end this unit with talking about replication and clustering. So first, I want to explain how replication works in MariaDB, and it's almost identical in MySQL, right? And to be fair, almost every database engine works like this, right? They have, the nuances are different, but for the most part, they all work very similar to what I'm going to show you here. So under normal circumstances, you have the database engine and you've got these table files that we were just talking about with our physical file replication, right? So you've got these table files. Every time somebody does something with the table, if they add new data, do updates or what have you, rows are being updated in that table and in the physical file, obviously, or in the buffer. Um, when we turn on replication on what's called our master, right? So with replication in MariaDB, you always have a master. The master is the MariaDB instance that is responsible for data definition language and data manipulation, not including selects, right? Well, it could include selects, but we're not worried about those. But all the other data manipulation, like update, insert, and delete, and so forth, creating users, create tables, altering tables, right? All of that stuff, and inserts and so forth. All of that stuff is handled by the master, and it is the master of all of those transactions. And when you set up the master, you're going to set up what's called a BinLog. We talked about how to turn on logging in this class. So we talked about the general log. We talked about the slow query log, right? We did talk about the bin log, but we didn't really play with it in the lab because we're going to do it in this lab. But basically, the bin log is it can get a little bit more granular than what we get in those SQL statement logs. So in the general log, every SQL statement gets logged in the general log. And in theory, if you wanted to, right? So if you think about this, if you wanted to sort of set up a poor man's replication, you could write a script that reads the general log and goes and runs all the statements from the general log in another instance of MariaDB, and you'll end up with a replication, right? Because every statement's going to get run, right? And you could be smart, you could filter out select statements, right? So you're only running, updates and inserts, and every time somebody runs an update or an insert on your primary server, your master server, you could have it go and run that in other servers. And that's essentially what replication does. That's essentially what it is, with the exception that that bin log isn't just statements; it can also be rows. So rather than outputting statements like we did with our general log, the bin log is row level, meaning that what it's actually logging is changes to rows. So every time any row in any table is modified, this could be a schema change, this could be deleting a row, adding a row, or updating a value within a row that's a column, right? Any of those changes are going to be logged granularly per row. So instead of the SQL statement, you get the row. This is a lot more efficient if you're going to replicate this to another server. If you think about it, a SQL statement is abstracted. It's a very abstract. SQL is I guess you might call it a fifth generation language, right? It's a fourth or fifth generation language. It's not quite plain English, but it's um, it's definitely abstracted. And one of the things that we saw in this class is that when you write a SQL statement, it has to, the database engine has to develop a query plan, and it has to get an execution plan, and then it has to kind of sort out how it's going to carry out the instructions that you gave it, right? It has to figure all that stuff out. So there's processing time that has to happen, and it doesn't always make the right decisions, right? Sometimes we have to give it hints, which we talked about when we talked about transactions in the previous unit. So the bin log that's at the row level, though, all it's saying is somebody already ran this transaction. Somebody already sorted out the best way to do these updates. All I'm going to do is tell you exactly what rows you need to change. So you just go through this list and you say, okay, row 5, 7, 9, 13, and 44, I have to change these column values, right? And that's it. So it's a lot faster, a lot more efficient to do it that way. So that is essentially what the bin log is. It doesn't have to be row level. You can set it up to be statement level if you like. Bin is short for binary, right? So it's not in ASCII, this log. It's not something that you can easily go look at, right? It's all in a binary file. But in any event, it's a row level output by not by default, but when you set it up, normally you would do that, right? Because if you wanted statement level and you weren't doing replication, you do a general log. But for replication, you certainly could do statement. It does work. You can set it to statement for that bin log. It'll work. It'll replicate. It'll be a little bit slower, and there are certain statements that can't be replicated, so you have to sort that out. Row level is definitely a lot more efficient, a lot easier to work with. So anyway, that's the first step, right? We're going to turn on that bin log. Then we're going to go and set up another MariaDB server, right? So we're going to set up a whole nother server. We're going to install it. We're going to do this in the lab, by the way. So in your practical assignment, you're going to start with your SQL server that you've been working with, the MySQL server you've been working with the whole semester, and you're going to create a snapshot of it, spin up a snapshot, delete the database in the snapshot, right? So we start from scratch. Start with a fresh database. And we're going to walk through this process of setting up what's called a slave, right? So you have a master, which I talked about, and then a slave is any database that's using that master as its source of truth for the row updates in its tables, in its individual tables for a particular database. So in any event, we're going to go spin up that other server, and when we're going to put some configuration options into that server that's going to spin up a new thread called server or slave IO. And what slave IO is going to do is it's going to go out to that bin log on the master. So periodically, maybe every X number of milliseconds, it's going to go out to the master and say to the bin log, do you have any new entries? Right? Here's the last entry I had. Show me the next, your next set of entries in your log. And then it's going to come back and say, okay, here's all the rows that have to get updated on your side. And it's going to put that into a slave relay file. So it's basically like the bin log, but it's on the slave, right? Then you have another process that's going to be running called the slave SQL or slave SQL process. its responsibility is to go look in that slave relay file, parse it out, and figure out what needs to be changed, and go and make those changes in the table in the background. So constantly in the background, the slave IO is going out and getting anything that's changed on the master based on what's in its bin log, and then putting it into this relay file on the slave, and then the slave SQL process is parsing that out and making those updates in the table itself. And in the meantime, users can be doing select statements, and they're just seeing the latest version of that data from whenever this replication happened, right? It's not real time, right? And I'll talk about that in a second. But it can be pretty close to real time, which you'll see in the lab. So all your data manipulation language and all your data definition language all has to happen on the master. You can do it on the slave. I think there are scenarios where that works, but generally it's best practice to limit DML and DDL with traditional MariaDB replication, to limit that to the master, and then the slave you would use for read only. There's really two purposes for doing this, right? For replication. The first purpose for replication is I just want to have a complete copy of my database running on another server in case the primary or the master goes down. Then everybody can roll over and the slave will become the master, right, at that point. So at least I'm still up and running. And then later on, we'll sort out those changes. We can flip-flop them at that point, right? Now the slave becomes the master, and we reconfigure the master as a slave, and then the next time the other one goes down, we swap it back, right? But it's very much a, kind of a failover mechanism. So that's one purpose for replication. The other purpose for replication could be high availability, right? So for certain applications, we might not have a lot of updates happening, right? It's mostly people reading the data. Think about something like Wikipedia, right? Probably 95, maybe 96% of the traffic for Wikipedia is people reading the Wikipedia pages. It's Wikipedia serving up content that exists in some database somewhere, right? That's probably 97%. My percent keeps going up, but you get the idea. It's the vast majority of traffic. Whereas the changes to that data is a very small percentage. So in that scenario, a master-slave scenario would make sense, because I'd have one master managing all of these updates to the data, and then replicating those out to hundreds of slaves, and then my application servers that are mostly serving out content over the web but aren't making any updates, they can read the data from many different slaves in many different locations. So I could be a user in Australia hitting Wikipedia, and I'm going through a slave that's in Australia, so it's much faster. But if I'm a user in Australia that needs to make updates to Wikipedia, maybe that's going to go to the master and it's going to be slower. I don't know how Wikipedia actually works. I'm just using it as an example. I know I'm probably going to get an email from somebody saying that's not how Wikipedia works. But it's just as an example, something that came to mind that could work like that, right? But that's an example. So again, two uses really for replication. One is for fault tolerance and for rolling over, for having a backup essentially, and the other one for high availability. So both scenarios would work. Now, in our little example here, we built this new server, but if we, a lot of times you're going to have this master has been running for a while, and you want to stand up a new slave, or maybe you're converting to replication, right? You say, okay, I've been running on one server for a while. Now I need to spin up my slave because I decided to turn on replication. This is going to be the scenario in your lab, right? You've been running this server all quarter. Now all of a sudden I'm asking you to set up a slave for replication, and you're going to have to get that data onto that slave. So how do we do that? Well, if you think about it, this bin log, once we turn on the bin log, it's going to start logging these transactions, right? And every time you do something in the database that does any manipulation of the data that's going to be required for replication, it's going to get logged into this bin log file. And at some point, in this process, we're going to create a SQL dump, and you can run the SQL dump command, the MySQL dump command, to not only create that dump, but also add the code to create a slave, right? All in one SQL dump. We're not going to do that in the lab because I want you to learn how to manually create a slave, but there is a switch for the MySQL dump utility that it not only creates the dump, but it also tells you that, here, when I created this dump file, this is the position that we are at in that bin log So once it gets restored to another server, it not only sets up that other server as a slave, but it tells it to go out to the bin log on the master and start building changes that were done since that SQL dumper created, as long as it's within the window that that bin log exists, right? If you wait too long and the bin log's been rotated, in other words, those entries are gone, then of course you're going to be missing a lot of those updates. So this is something that could be very temporal. But in any event, we do that MySQL dump. We generate that data. We know what position it should be at in the bin log. So now we've got transactions that are happening. We've got this. We're sitting with this MySQL dump file. Transactions have happened on the server. At some point, we're going to restore that dump file to the slave. The slave's going to come online, and then it's going to start processing everything from position 8 down. Even though more transactions are happening, it knows, okay, I got to go all the way back to position 8. Even though, right now we're position 22, I got to go back to position 8 and process all of those changes to the data because I'm only accurate up to position 8. So that's roughly how this works if you're going to build a new slave, which practically in the real world, almost every time you do this, you have to do something like this, unless you're starting completely from scratch. But even if you're starting, even in most scenarios, if you start from scratch, at some point you're going to have to add a slave, or you're going to have to swap your master with your slave, or this kind of stuff happens, and you have to know how to do this and know how to deal with this. One of the neat things about replication for MariaDB starting in version 10 is that it supports parallel threads. That's really important because, when I talked about this concept of high availability, right, having many different servers for simultaneous parallel reads, all of that goes away if you can't use parallel threads to apply those updates to all these other systems, right? If you think about it, MariaDB is already a parallel system, so the master is handling DDL and DML in parallel threads. So if it's a single thread that does those, that replicates those to our clients, to our slaves, then we have a bottleneck, right? So it is multi-threaded, right? So it allows parallel threads and multi-threaded in 10.1 or 10.1 and above, I'm pretty sure. One thing that's really important to note is this is asynchronous, right? So these processes are asynchronous, meaning they are not real time. They can be delayed. So you can't expect that, when an update happens on the master, you can't always trust it's going to be on the slave until some point in the future, right? So it's not good for real time applications that require those kinds of updates. And basically, pragmatically, what that means is committed transaction. So when you have a transaction on the master, it's going to tell the client that sent, if I'm a client and I send an insert statement to the server, it's going to come back and tell me that insert statement has been committed and is done, even though it hasn't gone to the slaves yet. So my assumption is the user, okay, this is the truth now. This has been inserted. This is what everybody understands about this data. But the reality is the slaves don't know about it yet. They will at some point in the future know about it, but they may not know about it yet. So that's some of the drawbacks of replication. And this is where clustering comes in, right? So clustering is very similar to replication with one major difference. The first being that it's synchronous, meaning there is no delay. So what that means, how that's different, is transactions are not considered complete until there's a quorum. In other words, until they are consistent across all nodes. So if you have 10 nodes in your cluster, when you send an insert statement to any one of those nodes, that statement's not going to be considered complete until every single node has that information, until every single node has updated, and the files thus have been updated. So that's a major difference, right? So it's real time. There is no master with clustering. There's a primary, which is, I guess you could say it's similar to a master, the idea of a primary node. However, it's not, it's not in the sense that the master controls everything, right? Anybody can handle any transaction in a cluster. The primary's job is not necessarily to handle all the transactions. It's simply to coordinate nodes joining and leaving the cluster, right? It's not really, it's not the responsible party for all of these transactions. Anyone can be responsible. Anybody can receive a transaction and ensure that it's replicated to all the other nodes, and then and all that other stuff, right? So it's a and really, MariaDB does support multi-master replication, which I guess you could say is similar, but this is just a core This is just core functionality with clustering that's supported. So the failure of any primary node also means that any other node can just take over that role. You don't necessarily have to do any work for that to happen, right? That's just going to happen in the background. Hopefully, if you have a good clustering algorithm, right? That's going to happen in the background. And it just so happens that the clustering mechanism in MariaDB is Galera. This is what MariaDB includes. It was included in MariaDB 10.1 and later, which means there's nothing you have to install. There's nothing you have to download or that you have to build or from sources or anything like that, which means it's super easy to set up. It's already baked into MariaDB, and you're going to see that in the lab. We're not going to have to do anything crazy. And by the way, I have to tell you that was one of the things I love about MariaDB is that replication is so easy to set up with this API. It's if you use something, I'll give you an example in Microsoft SQL Server. Um, Microsoft SQL Server, up until they had Always On, which is a feature they have that works very similar to Galera. Up until then, if you wanted to set up a cluster, a true cluster, you had to have a shared storage platform, and it couldn't be a NAS. It had to be a SAN, and you had to do some tricks with, the operating system to get that to work, and it was always a nightmare to set up. So this is clearly a lot easier now. Not to badmouth Microsoft too much, they definitely improved this with their always on functionality, which is it's sort of replication that's real time always on. And it's a little more similar to clustering. It's not true clustering though, for a variety of reasons. But we're not learning about Microsoft here, so I'll leave that for another time. There are some caveats for Galera. It only supports InnoDB. So if you're using MyISAM, it's a non-starter. You can't use it with Aria, right? So these other database engines that we talked about, it's not going to work. It's got to be InnoDB. There are some statement types that may not be supported. There's a list of them in the documentation that you can take a look at. You have to have a minimum of 3 servers to guarantee that it's crash safe. In other words, if you just have 2 servers, there could be some issues with that, so they recommend 3 or more. And really, it's a good idea to use an odd number of nodes. If you have an even number of nodes, then there are scenarios where you can't reach a quorum. In other words, there's no tiebreaker, right? Think about a company with a board of directors where it's 4 people, right? There's never gonna, you can always have a tie if there's 4 people on the board. But if you have 5 people on the board, as long as everyone always votes, you can never have a tie, right? Um, unless somebody abstains from voting. So it's definitely a little bit more, a little bit more robust when you have an odd number. Doesn't have to be a huge number, right? And that reminds me that, nice thing about Galera is that there is no, you can have a lot of nodes. You can have 100 nodes if you wanted to with Galera. But again, important thing about this to remember too, though, is that the storage is also replicated, right? So if you have a huge database, every node's going to need its own storage, and it's going to basically be a full copy of the database. So there is some scalability issues that you might have with something like this to be aware of. It also requires the right set replication or WSRep API. And again, this gets installed automatically with the latest version of MariaDB. So all of you have it because I'm assuming everyone in the class has 10.1 or later for MariaDB. So you're going to find that you already have that. You're not going to have to install it or build it or download it or use apt-get or anything like that. The other caveat that I forgot to put on here that's important to mention is that this only works in Linux. You cannot do this with Windows. So MariaDB runs in Windows, but you cannot do clustering with MariaDB in Windows using this toolkit. So that's another big caveat to be aware of. But luckily, we're using Linux for our labs, so it works fine. All right, so at just about an hour, that wraps up this unit's material. Thanks for hanging in there. And if you have any questions, let me know. Thank you.